Okay, so I'm kind of curious about this. D-Wave Qubits 2025 Advantage to Performance Preview by Farre at D-Wave. Let's go. One comment here. Yeah, baby! D-Wave is the future! Let's see what they gotta say.
During the past few months, we've been calibrating a new exciting system. It's Advantage 2 at the Z12 scale, and I've been able to test its performance, and I want to tell you about it.
Let's go.
This is the biggest Advantage 2 system that we've built. It's an early calibration with 4,600 qubits and 41,000 couplers. And Advantage 2 processors feature the Zephyr layout with connectivity 20. This is a step up from our previous layout, Pegasus, in Advantage 1 processors that has connectivity 15. And this allows...
Okay, I'm guessing connectivity 20 means that each qubit can connect to 20 other qubits. Each early calibration with 4,600 qubits and over 4,100 couplers. I don't know what couplers are. Let's see.
Allows us to embed more interesting interconnected problems.
Okay.
Some interesting features about Zephyr is that every qubit in the Zephyr layout is involved in several cliques that are native and they're of size 4. This means 4 qubits talking to each other, as well as complete bipartite graphs with 8 qubits on each side. So this is not only interesting for mapping complex optimization problems, but this is also good for machine learning architectures. The Advantage 2 system also features 40%.
Machine learning architectures, again, just a refresher, there are 2 to 3 things that are implied when they say machine learning architecture. One is to use quantum computing in order to speed up the cost function. Another one is some sort of hybrid of actually using quantum neurons and then doing full-blown quantum neurons. So which of these 3, I don't know. And maybe there needs to be a way of clarifying these 3. But I think typically when they say this now, because we're so far away from having quantum memory and quantum neurons, I think they're just talking about speeding up the cost function with quantum algorithms.
% higher energy scales. In our quantum computers, we map optimization objectives to energy. And higher energy scales means greater separation between good solutions and worse solutions, making good solutions more likely.
Right. Okay.
The Advantage 2 system also has twice the coherence time of Advantage.
Good.
And this means that it can perform a disturbed coherent evolution for twice as long. And this makes the quantum annealing algorithm more effective.
So it means that you can perform potentially twice as many results, or you can do a more involved calculation, or you can get cleaner results from the same calculation. So overall, twice the coherence time is a good thing. You want it to be as large as possible. 80% higher energy scales. I'm not exactly sure what that means, but because it's an annealer, maybe these 2 things are related, that because you've got 40% higher energy scales, the coherence time is twice as... So I don't know what the first one means.
And the Advantage 2 system also has 4 times lower flux noise. Flux noise translates into imprecision on the problem that you're sending to the QPU. And this means that the QPU is solving a problem that is slightly different from the problem that you wanted to solve.
QPU is quantum processing unit, just like a CPU, so he's talking about quantum computing.
Reducing flux noise means being able to solve higher precision problems.
Okay.
Let's dive into some performance results.
Again, I'm not sure what flux noise means.
not all equal 3SAT is an NP-complete Boolean optimization problem class where you have a number of variables and a number of clauses. And each clause has 3 variables or negations of a variable each. And the goal is that these three objects on each clause need to evaluate to not all equal. This means they cannot all be true at the same time, they cannot all be false at the same time. It has to be a combination of both, like true, false, false. And the way that we map this to our quantum annealers is we go clause by clause, and we set ferromagnetic or antiferromagnetic coupling between the variables. And we add all the variables, getting a total Ising Hamiltonian. And by the way, this problem class is defined by the density or the ratio of clauses to variables. And in this case, it's 3. If this Hamiltonian is not a subgraph of our QPUs, the way that we map it to the QPUs is a process that we call minor embedding, in which we use several qubits in a chain of qubits to represent a variable. This is how this problem maps to the Advantage 1 system that uses the Pegasus layout. And this is how the...
Okay, so null equal Ising Hamiltonian embedded on Advantage system. Instance is mapped to Ising Hamiltonian embedded on Advantage 2 system. Oh, so how they embed it, how it looks different. Okay.
The problem embeds into the Advantage 2 system that uses the Zephyr layout. And these are chain length statistics of mapping problems of different sizes to Advantage and Advantage 2.
Chain length statistics of mapping Advantage and Advantage 2. So orange is Advantage 2, blue is Advantage 1. Higher connectivity provides more compact embeddings. So the mean chain length versus the problem size. So as the problem size gets larger, the mean chain length in Advantage 2 is lower. So it needs less resources, which means, I guess, less noise.
Advantage 2 is able to embed these problems with lower chain length. And this is thanks to the Zephyr processor, the Zephyr topology that has higher connectivity, and this allows us to map these problems more compactly.
Okay.
And shorter chains means better performance of our QPUs.
And just a reminder, D-Wave does quantum annealer, or what they call a quantum annealing computer. It's not a universal quantum computer. It uses a different architecture which allows it to have less noise, more qubits, but it can solve fewer algorithms. So it's like an ASIC chip. It's more specific. And there's nothing wrong with that. That's perfectly acceptable. In fact, it's highly intelligent because these are the first, I guess, quantum computing architectures which have demonstrated the ability to solve useful problems faster than a classical computer.
So here results when sending these problems to the Advantage 2 processor and Advantage, asking for 200 microsecond anneals and 5 reads, 1 program in per problem. And this is percentage of optimal. We want these values to be the higher possible. And every point over the diagonal, it means that Advantage 2 got closer to optimal than Advantage.
Okay.
And here, you'll see that there's 2 colors. Black shows the sample minimum out of 1,000 reads, and gray is the sample median out of 1,000 reads. And all the points, or most of the points, are over the diagonal, meaning that the advantage 2 system outperforms the advantage system most of the time.
Okay.
Here's another optimization problem. It's called the binary paint shop problem.
Okay.
And in this problem, you have a number of cars, 3 in this example. So there's 3 different cars that appear twice in a queue. And this queue goes into a paint shop, and you want to paint each car with 2 colors. And the goal is to change the paint in the machine as few times as possible. Here's a greedy solution to this problem that consists on avoiding changing the paint unless you find a car that was already painted with the current paint, and that forces you to change paint. And this is an optimal solution to this problem that uses less paint changes, 2 instead of 3.
Well, I'm not sure I
This is how
follow
advantage.
because it's cars appear twice in a queue. Okay. They need 2 paint colors. Okay, so the 6 cars. All 6 are made up of 3 sets of duplicates, and I need to paint each of those duplicates a different color. And so that's why the optimal solution is you paint 1 color, you switch, you paint 3 in a row, you switch, and then you paint the last 2. And so essentially, yeah, 3 cars, 1 color, 3 cars, another color. And again, I'm kind of confused because wouldn't the optimal solution be 3 cars, 1 color, and then switch, and then you paint the other 3 cars the other colors? So just 1 paint change. So I'm not sure I'm understanding the problem.
1 and advantage 2 systems perform on this problem when asking the QPUs for 500 microsecond anneals and 1,000 reads. Again, 1 programming per problem. These lines, well, on the y-axis we have relative error, and we want this value to be the smallest possible. If you got relative error of 0, that means that you found the optimal solution. These lines go through the median over a collection of problems per size. The dashed lines show the sample minimums out of these calls of 1,000 reads. And advantage 2 is able to find the optimal solution for larger problems than advantage. And the solid line.
So here we have number of cars, and here we have relative error. So the larger the number of cars, as you'd expect, the number of relative errors goes up to a certain amount. It is logarithmic, but still it tapers off. Solution quality. So that is surprising. It seems to indicate that above a certain amount the errors don't grow. So again, I feel like I'm missing something here. Advantage 2, dash line, solid line. It's not very well explained.
Lines show the sample median out of 1,000 reads, and advantage 2 is closer to optimal than advantage throughout all these problem sizes.
What?
And just to relate relative error to the original problem, let's look at a 300 car instance. This is the optimal solution for 300 cars, 84 paint changes. This is what advantage 2 found. This is the next best, 85 paint changes, This is
Okay.
what advantage 1 finds. And this is 96 pane changes. This is the median solution of advantage, and advantage 2 does better than that all the time.
Question, how do you determine the output? The classical computer?
I mean,
Yes, you can run a classical computer
I don't
for much
fully
longer.
understand
And if you find agreement, then yes.
the problem, but just accepting that I'm moving on.
And this is a greedy solution, again, following this scheme where you avoid changing pane until you find yourself forced to change it quite frequently. And it's 141 pane changes that would be over here. So QPUs do better than that systematically. And the Advantage 2 system is outperforming the Advantage system with all these metrics. Here is the mean chain length. of
That's not
embedding these
obvious. It's not
problems.
clear.
Advantage 2 is able to embed them with shorter chain lengths. And again, this helps the performance of our quantum computers.
With shorter chain lengths.
All right, so this is a very interesting feature that we've released this last year. It's called fast anneals. Fast anneals allow us to run problems much faster than before. The shortest annealing time when you run a standard anneal is half a microsecond. The shortest annealing time with fast anneals is 5 nanoseconds. And fast anneals and standard anneals, they use a slightly different protocol, dashed lines versus solid lines here. And the
Okay.
linear biases of your problem in fast anneals need to be implemented through auxiliary qubits. But if you run fast anneals and standard anneals for the same time, the performance is very similar. Here is solution quality versus annealing time, the lower the better, of a QPU that's been subjected to different physical temperatures. If we look at the longest anneals, you'll see that raising the temperature of the QPU has quite a dramatic effect. It makes solutions worse. But as we go towards faster and faster anneals, this effect starts to mitigate until it disappears completely. When we're in fast anneals, we run so fast that we can outrun thermal effects. And this allows for the undisturbed coherent evolution of the Hamiltonian. If you run for longer, then temperature starts to kick in. This is what we call the out of equilibrium regime. And if you run for even longer, then this is the quasi-static regime, where typically solutions do well thanks to the slower thermal relaxation towards the optimal.
Quasi-static regime.
It's thanks to fast anneals that we
I'm
got
not following this.
some very nice results. Here on the left, we have the simulation of the coherent behavior of a 2,000 qubit Ising chain.
Okay.
And this is the fast annealing regime. And in the fast annealing regime, we find a complete agreement between coherent theory and the results that we get from the QPU. And similar to what I was sharing
Okay.
in the previous slide, if we anneal for longer and we subject the QPU to different physical temperatures, then we can see a deviation from that. On the right is our quantum supremacy result, in which we reproduce the coherent evolution of quantum spin glasses at a scale that is intractable for classical methods. And I think that my colleague Andrew King is going to talk about this later. Again, these results are done in the fast annealing regime. All right, so let's get back to comparing Advantage 1 and Advantage 2. These problems are no longer minor embedded problems. This is just taking the intersection between the two chips. If you take the intersection between a Pegasus layout and a Zephyr layout, what you get is a chimera graph. And in this chimera graph, we set precision 100 spin glass weights. This means random positive, negative weights where the smallest one has a magnitude of 1 over 100. And here we have relative error, the lower the better, for a range of annealing times. These are statistics over a collection of problems and also over taking 1,000 reads.
What?
This is the light boxes are the medians, and the bold boxes are the sample minimas over.
Okay, this is where it starts to feel a little bit like gobbledygook. If I understood correctly, these over here are the physical chip sizes, and so with advantage 2, your chip size is even smaller, and then randomly it outperforms the advantage system in something. I don't understand. Precision 100 spin glasses. It's it's a bit of a mystery. I'm not following exactly what he's doing.
Over this ensemble of problems. And there's a number of interesting things in this plot. One of them is that the coherent the coherent out of equilibrium and quasi-static regimes are quite apparent. And advantage 2 is doing better than advantage for all problem size, for all annealing times.
For all annealing
But what I find fascinating is that if you look at the best solution that advantage 1 is able to get, there's a solution in the quasi-static regime for 500 microseconds. This solution is matched by advantage 2 over 10,000 times earlier in the coherent regime. So this is
so the annealing time is 10,000 smaller for the relative error. This just looks like a random line. I'm not getting the physical intuition over here. So in order to get the annealing error down here, you increase the annealing time. And see, essentially you can run experiments much faster for a stated error. Wow. I'm guessing that's what he's saying. So, yeah.
more than 10,000 times speed up in annealing time on this type of problems.
That's what it sounds like.
These problems are embedded. This is the largest 3D lattice that we can embed on both chips, advantage 1 and advantage 2 at the Z12 scale.
Okay.
There is a cube of 12 by 12 by 12, and both QPUs are able to embed this problem using chain length 2. So the chain length statistics are the same for both systems in this case. And we set precision 100 spin glass weights to this problem, and here's the
So if you've forgotten what chain length 2 is, so have I. I'm not exactly sure.
solution quality again. And the story is similar than before. We see advantage 2 descending quite steeply towards optimal. It gets pretty close, and then temperature starts to kick in. Results get worse. And then if we let it run for longer, results get better again in the quasi-static regime. And again, if you look at the solution, the best solution that advantage 1 is able to get in the quasi-static regime, advantage 2 is able to get it over 10,000 times faster. In conclusion,
Okay.
the advantage 2 system at the Z12 scale clearly outperforms the advantage system. And that's it from me. Thank you.
Wow. Okay, that was very, very difficult to follow. man. It's an exciting result. He doesn't make it sound exciting. Um, I I wish they had presented this more clearly. Um, but yeah, I'm gonna have to go away and just let it sink in and think about it some more and just keep watching this and other videos like this, and eventually it'll sink in. But yeah, at first appearances, the problem was not very clearly laid out, and even if I just accepted that, okay, I'll come back to it and figure it out, the problem was not well laid out. So I'm gonna have to look that up on my own. I'm sure he's missing some key requirement or key constraint that I'm not getting, and how is that problem converted into an Ising Hamiltonian? That's missing. Like, again, this could be a lecture. It doesn't need to be so quick. It can be an hour, and it can be an entertaining hour if things are broken down really nicely. Kind of like Feynman. You listen to Feynman for an hour. Remember when you were, when you were a teenager, an hour of Feynman's lectures would be quite enthralling because, like, at every segment you feel like you're getting smarter, you're understanding, the connections are being made. So over here, it just like it's really like feels like pulling teeth. So it seems like it's a great result. Should be better explained. I don't know how to take this. Like, I wouldn't know how to take this and apply it to my problem set. So that should be made easier.